Hello everyone, thanks for coming back for another one. This equation should look very familiar from chapter 6. And so obviously, excuse me, or not, the topic is heat flow. And the heat that's moving from a hot object to a cold object is calculated by the mass of the object, the change in temperature of the object or sample, and the specific heat or the specific heat capacity. Sometimes I've seen little s's down here or little m's down here, the molar heat capacity. Or sometimes this capital C is a small case c. But in any case, it's some number that's constant and specific to that substance that's heating or cooling. The delta T is just the ending minus beginning temperature. The mass is usually in grams, and the specific heat capacity is probably given to you. And you just multiply the three together. How much more simple does it get than that? I don't know. So if I have 200 grams and the specific heat capacity of water is 4.18 joules per gram degree Celsius, the grams cancel, and ending minus beginning, oh yeah, that would be a negative. Heat's released. Well, how much heat is released by the water cooling? Right, okay, so the water cools, gives off the heat somewhere else. Yeah. We've got to be careful with the negatives. Sometimes I'll throw in negatives or change the negative to a positive just because I know the conventions of heat flow, which you might also remember from chapter 6, or you might not. The molar heat capacity, you could say, is the heat needed to raise 1 gram of that substance. Oh no. The heat capacity is the heat energy needed to raise 1 gram of that substance 1 degree Celsius. For water, it's 4.18 joules per gram degree Celsius. Similarly, the molar heat capacity, not trying to confuse you, but sometimes it's given in moles instead of grams. In other words, we just have to change grams to moles for that specific substance. So here it says the molar heat capacity for an alcohol, 113 joule per mole degree Celsius. Well, it would be pretty easy to change moles to grams. If I added up 2 carbons, 6 hydrogens, and 1 oxygen, I could easily convert this molar heat capacity into a gram or mass heat capacity. But it's one, oh, right. Oh, yeah. So if I'm given grams, I need to make the grams and the moles match up. So I could either convert this to joules per gram degree Celsius or change this grams to moles. So the molar mass of that alcohol is 46 grams. 125 divided by 46 is 2.72 moles. So if that's the number of moles of particles I have, take it times the molar heat capacity and also still the change in temperature. Oh yeah, usually these numbers come out large. The constant may be given in joules, but the answer is almost always reported in kilojoules. Just move the decimal 3 places. A lot of heat constants thrown around in enthalpy and heat considerations. But when we change state from one solid to a liquid, liquid to a gas, gas to a solid or whatever, there's some heat associated with that. And often we'll put little subscripts on the H, the enthalpy or heat, to try to describe what's happening. So if I wrote VAP, that stands for vaporization. So if I had 1 gram of liquid water at 100 degrees ready to boil, I add the heat of vaporization, and that changes the gram of liquid water into a gram of gaseous water at 100. Conversely, if I'm going back the other way, condensation, or COND perhaps, depends who you look, depends who writes it, depends who's talking about it. So I have vaporization and condensation, and those numbers are of course exactly the same. This little slide talked about per 1 gram, but what if I didn't talk about 1 gram? What if I talked about 1 mole? Well, all you have to do is change grams of water into moles of water, and there you have it. So I took 1 mole of water. I took the grams, changed them into moles, and get this number here. So kilojoules per mole. 1 mole of liquid water ready to boil. Add the molar heat of vaporization to get it into a gas, or if you had a gas, take away the molar heat of condensation. So in essence, they're labeled different things, but they're the same. They're the same number. One's negative, one's positive. They're opposites of each other. Vaporization, condensation. So if I were to look at a heating curve for, say, water, no, this isn't water. How do I know this isn't water? What happens to the temperature of water as it boils? Nothing. Trick question, but it's at 100 degrees. But nothing's boiling here. It looks like I'm boiling at 140 and melting at like 70-ish. So yeah, what happens to the temperature of ice as it melts? Nothing. What happens to the temperature of a substance as it boils? Nothing. So here the delta T would be 0. Here the delta T would be 0. So here I'm using the moles times the molar heat of fusion, or the moles times the molar heat of vaporization. And I use the Q equals M times C times delta T for the calculation in these regions, whether I have a solid, liquid, and even a gas sometimes, although it's more difficult to apply there. Sometimes it's good to think about the structure of the particles, molecules, ions, solid, liquid, gas, and you can fill in the blank here if you want to. Just another pretty little diagram I clipped off the web. Ice, a mixture of ice and water. Water, a mixture of water and steam. While I'm boiling, nothing happens to the temperature. While I'm melting, nothing happens to the temperature. But in the warming regions of solid, liquid, gas, of course. Nothing much to say about that one. And yet another just pretty picture diagram based on what we know about solids, liquids, and gases, freezing and melting, condensing and boiling. There's also another one for going from a solid to a gas, or a gas to a solid. There's an amount of heat for that as well. Let me look at this one for a second. So, sometimes I like to draw out a picture for myself, imagining what the heating and cooling or phase change might look like. So if I had what am I talking about? I'm talking about water. 500 grams of water, 500 milliliters of water. I go from 50 to 100, at which point it starts to boil. This is the boiling portion of the curve. And then I collect the steam and go from 100 to 120. So that's Q equals M times C times delta T. Specific heat capacity of steam is different than the specific heat capacity, the molar heat capacity of steam, molar heat capacity of water. I must have changed 4.18 times 18 grams per mole gives you 75.3. And the change in temperature here, 100 to 50. Here I just made them all positive, knowing that I'm going to have to add these, sum total all these up together and find the total heat needed to be added to do that. Looks like the total sum comes out to probably 1,256-ish. Right? 27. Yeah, right. Okay, cool. So this one times this one, this one times this one, then this one times this one times this one. This is in joules, this is in joules. This came out to be a big number. I changed it to kilojoules, but I better add them all together in kilojoules to make sure I'm consistent. These are big numbers too. What am I talking about? So this is in joules, that's in kilojoules, that's in joules. So just make sure you add them together all in joules or kilojoules, but usually it's kilojoules because the numbers are usually so big. Similar heats for phase changes: heat of fusion, heat of crystallization. Fusion means to melt, crystallization means to freeze, but they're the same number. One's adding heat, one's taking heat away from the solid. Add heat to the solid to melt. Remove heat energy from the liquid to make it freeze. Molar heat of fusion, I can do this, play the same game, just changing grams to moles. So don't be confused, but do analyze carefully what constants are given, what the units are, and the units are the hint with regards to how to deal with it, how to work with it. I think this just summarizes the first couple phase change constants I gave: vaporization, condensation, or fusion and crystallization. Excuse me, goodness gracious. what's the heat required to convert 150 grams of ice at -10 to water at 40? Well, if you're really motivated, you'd pause this right now and figure that out by yourself and then check my answer. But if you're in a hurry, like we always are, but at some point you got to practice this, right? So another silly example, if you'd like to look at it, nothing is different. Ooh, too far. Go up. There we go. Nothing is different. This is the molar heat of fusion and the molar specific heat capacity. And I change grams to moles so that moles would cancel. Temperature change from -10 to 0. 8.33 moles. That's 150 grams divided by 18 grams per mole times the kilojoules per mole for melting. And then from 0 to 40 to warm it up is 40 degrees change. And the molar heat capacity of water and the moles of water. Interesting. Not after you've seen about 5 or 6 or 7 of those. But good to practice. One last idea. There's also the possibility of subliming, going from a solid to a gas or a gas to a solid. This happens all the time with iodine and carbon dioxide, more rarely with water though, but it does happen. Snow on a dry winter day, even if it does not warm up above freezing, can still sublime into the gas. Or then at night, when the air temperature drops even further, water vapor from the air will condense onto the windshield of your car directly from a gas to a solid without ever really changing to a liquid much. Maybe that's because your glass on your windshield is so cold, and it's also because cold air can't hold as much water vapor as the warm air. But in any case, heat of sublimation, heat of condensation, these two numbers will be the same. On this one I would just add the heat of sublimation to go from a solid to a gas. Here if I had a gas I would remove the heat of sublimation, or you could say heat of condensation, or I call it deposition actually. I've heard that more commonly. In this silly little demonstration they have some solid iodine in the bottom. They warm it into a iodine vapor. It goes from a solid to a gas. When the gas floats up here and touches this cold ice containing flask, it recondenses into a redeposits, I should say, is what I usually say. I say usually condensing. I think of condensing as going from a gas to a liquid, but gas to a solid I call it deposition. Oh yeah, there's this one too. Sometimes we'll use the heat equation to equate heat gained by one object to heat lost by another. If I take a very hot coin being warmed in a flame and drop it right in some water and measure how much water I have and how the temperature of the water increases, I can easily estimate the temperature of the flame. So if I know the mass of the coin, a penny weighs about 3.1 grams, making an old penny that weighs, it's mostly made of copper, and the specific heat of copper, and the change in temperature I don't quite know. I know the final temperature of the coin is the same temperature as the water, but the initial temperature of the coin, that's what I'm trying to figure out. Similarly here, I do measure the initial and final temperature of water, 50 grams of water. I've 1 penny dropped into 50 grams of water, and so this one times this one is 1.194. This one times this one is 209. Now I need to solve for some unknowns here. I just have one unknown though. I measure the ending and beginning temperature of the water. I know that the ending temperature of the coin is the same as the ending temperature of the water. So then I just try to do my best with some algebra and solve for the temperature of the fire. This one came out to 875 degrees, or about 900, with just 1 or 2 sig figs. Alright, finally, that's all. Thanks guys, I'll see you in class or in discussion soon. Thanks for all your hard work.